Hello, my name is Simon. Nice to meet you too. So apparently I can into internet now. Wait, how do I even have 2 subscribers? Wait, I don't even have any videos yet. So I decided for my first video that I'd get some last minute physics homework out of the way. We're doing the Doppler effect. Don't ask.
I don't care if anybody gets it, I'm going as the Doppler effect.
So the Doppler effect, according to Google, is an increase or decrease in the frequency of sound, light, or other waves as the source and observer move toward or away from each other. The effect causes a sudden change in pitch, noise, and passing sound. Where am I? Alright, so beside that boringness, the Doppler effect actually is...
It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Shut up! Oh wait, that's a good point. But what does that entail? Let's find out. Before we can understand the Doppler effect, we have to understand how sound works. You see, sound is a wave. It has peaks and troughs that occur in a repeating cycle known as a period. If you know what I mean. Everyone, meet Doocy. He makes idiotic complaints all the time. Ignore him. As I was saying before I was rudely interrupted, unlike other waveforms such as water and light, which are transverse waves, sound is what is referred to as a longitudinal wave. This is because sound is just a series of vibrations moving through the air or wherever when, eventually, it reaches your ears where your brain turns it into something that we can understand. Well, that wasn't convoluted at all. And remember, sound can come from anything that vibrates. Anything! Or at least anything that's made out of matter. So with that out of the way, let's get back to the topic in hand. The Doppler effect. By the way, by chance, does anybody know who actually discovered the Doppler effect? Anyone at all? Wait a minute.
Choo-choo train?
Close!
As seen in this very oversimplified model, sound coming from a source would typically look something like this, something like concentric circles. Each white circle emanating from the sound source represents sound being made with a frequency of 1 second. Frequency, by the way, is just the length between 2 peaks, or 2 troughs. Now look what happens when the source is moving. It should be obvious just by looking that the waves that are coming in from this side are a lot more densely packed and thus more frequent than the waves coming in from this side. Because our ears don't know and don't care if a sound source is moving or not, we'll interpret the more frequent sound on the left as having a higher inherent frequency, and thus it sounds higher pitched. Conversely, the sound on the right will sound lower pitched. There are hundreds of examples of the Doppler effect in real life, such as this ambulance in Rotterdam in the Netherlands, and this example from the Big Bang Theory.
No, it's not. If I have to, I can demonstrate.
Interestingly, if the sound source was moving at the speed of sound, you wouldn't be able to hear it if it was coming towards you. Only once it is past you will you ever be able to hear it. Apparently this is the formula that's used for calculating Doppler effect frequency. Intense, right? Alright, so I hope you were edumacated by this short little thing that I made for my science class. Well, that was fun. I could finally check that thing off my checklist. I need a break. Let's see what's on YouTube. Oh wait,